To be here, and thanks so much, Sid, for organizing this great initiative. So I'm here today. I'm a professor at UCLA, and I lead the Visual Machines group. Just in one sentence, what we do is computer vision, but we take a special approach where we look at the symbiosis between the camera sensor itself and a deep learning model. So these two are organically fused, and that's what makes our approach unique. And so in that way, what you're really doing is you're combining the physical model of the process with some sort of data-driven model of inference. Okay. So I've prepared a very short talk. It's a short talk so we can have some discussion. And I'll sort of just jump right into what it means to be an artificial physicist. So here we have one of my graduate students, and he's tossing a paper, maybe his latest exam score, and he's tossing it into the trash can. Right? And what you have seen here is you see the first 3 frames of the video. Now, given these first 3 frames of the video, do you guys think it's going to go long? It's going to go past the wastebasket? Is it going to go short? Is it going to not reach the wastebasket? Or is it a bullseye? Short. Okay, almost everyone says it's short. Our human understanding of having thrown away so many bad exam results tells us that. But something else tells us that, and that's high school physics. So if we go back to high school physics, we have these orthogonal kinematic equations, right? X equals x naught plus vxt, y equals y naught minus half gt squared, so on and so forth. All the stuff that we needed to get into college well, I went to school in America, but I'm sure you guys need to do this for your qualifying exams as well. But we can apply this analysis to these first 3 frames. We can fit at least squares to this problem, right? There's 2 unknowns fundamentally. So you have 3 frames of data, 2 unknowns. You can solve this, and maybe you could get a physical estimate of the trajectory of that exam score. So here's what happens if you take that result. So we're going to take the first 3 frames, and now we're going to predict frames 4, 5, 6, 7, all the way up to 18. And if you see, that's the prediction. We predict it's going to go a little bit long based on the physics alone. So you see this nice, neat parabola, but as so many of you correctly guessed, it's short, right? So there's a mismatch between the physical prediction and the observed trajectory. Why do you think that mismatch happens? Air resistance, right? It's not crumpled up into a nice, tight ball. It's kind of loosely crumpled up. Maybe there's some spin. Who knows? It's going to be some really difficult physics to model exactly where this thing would go. So we appeal to the sort of the engine of our generation, which is Resnet, for example. You take these 3 frames, you have the student, fail 64 more exams so he can get a training set, and essentially build up a training set of data and feed it into a pattern recognition algorithm like Resnet. And so your input might be the initial trajectory of 3 frames, and the output in the training phase would be labels of where that paper ball was in pixel coordinates, right? Standard computer vision approach, nothing special here. And if you apply this analysis, you end up with a result that looks like this. And so the optimist might look at this and say, you know what, the termination point matches with ground truth, I'm done, so let me go write a CVPR paper, right? That's what the optimist will say. But in reality, what's happening is we see a clear mismatch between what our physical understanding of the laws of physics tell us and what the result is. Specifically, the 4th frame of this prediction, right? The first orange ball to the rightmost that you guys are viewing, that one is so far away from where the paper ball is at that state that it's just an impossible trajectory to have. Why should the neural network predict something that we know is impossible? That solution should be pruned out. But unfortunately, with these existing models, it's not. And it's not a flaw of Resnet alone. To be fair, what we did was we gave it terrible training data. We gave it terrible training data of one sort of ideal type of toss, and it overfit. It overfit to the training data it had, so it doesn't adjust to the new types of trajectories that you see. So what I'm hinting at here is a new form of playbook, right? This is the scholarly playbook. A lot of the talks have alluded to it today, and that's to work at the seam line of physics and neural networks. So if you combine your physical understanding with networks, you might end up with a result that looks like this. And so, of course, here there's 2 pixels of error, right? The trajectory is predicted with some accuracy. And so this playbook doesn't just apply to tossing balls. We can rethink a lot of different problems. The field that is closest to my own is imaging sciences, right? Various types of imaging. And we can form a plot to look at how good the data is versus how good the physics is. So if we have a lot of data and we don't know anything about the physics, then sure, you might want to go use Resnet. On the other hand, if you know nothing about the data, you have no data, but you already have a very good physical model, you have like an n=1 instance, then you just apply the physical solution. Right? But really interesting engineering problems are in that midsection region, that middle where you have some amount of data, right? Some partial data and some partial understanding of physics. And that's where physics-based learning comes into play. And that's where physics-based learning comes into play to work at this seam line. So the answer is not so simple as you just blend physics and learning. Unfortunately, neural networks are inherently unstructured. There's no plug-and-play package that says, you know what, go put this equation in and the neural network will try to solve this output. There are many ways to overcome this hurdle, of course, and our group is looking at quite a number of networks. So for example, residual learning, multi-stream inputs, constrained networks, so constrain the manifold that the neural network searches to only search for physically realizable solutions, student-teacher models, and so on. Without going into the details of the networks in the interest of time, I mean, maybe I can go through one of them. Like, if you go through the top left, like what is a residual learning model, right? Residual learning is a very simple idea. It's been applied to other domains, but not typically physical solutions. So the idea is basically you train your neural network to learn the null space of physics. The null space of physics is the model mismatch that physics alone could not predict. So if you look at that trajectory of the ball trajectory was not exact, right? But you still got a nice parabola and it was somewhat close. You missed a little bit long and the ground truth was a little bit short, but overall you got that same trajectory. So maybe you could just have the neural network do a correction of the physics prediction, right? So that correction is going to be like a smaller value and something that's easier to predict. Maybe you could also use the physical inputs, and have different types of input conditions as well. And so the model here, of course, is going to depend on how good your physics is. If your physics is very poor, then your residual might actually be larger than as if you started with a zero initialization. So there's some subtlety in how you select which model that you're going to use. But if I were to pop up a level and look at this problem in another way, you have the era of the traditional physicist. Does anyone know whose picture is on the left? Isaac Newton. So for one bonus point on an exam that doesn't exist, who is the picture on the right? So I can't hear? You have to shout it out. No, it's not Laplace. No, it's not Leibniz. So you can see how much less famous Leibniz is, I guess, than Newton by that statement. But it's actually a Fresnel. Fresnel, also around that time, is a very famous scientist who's responsible for many, many inventions related to light. Fresnel wave propagation. In Germany, a lot of their centers are named after Fresnel, even though he was French. So Fresnel has done a lot of great work that has fundamentally shaped how we look at light transport and the mathematics that underlie light. And the reason I bring this up is that a lot of our research at UCLA focuses on the subtlety and the beauty of light, but light is also a very difficult problem to analyze. When you look at this plot again, and you look at the goodness of physics on the y-axis, unfortunately, many of the models that we have for light, this is why we don't learn it in high school as deeply as mechanics. A lot of the models we have for how light behaves actually misbehave. The models are not terribly accurate. Okay? And so what that means is that you're playing in a very dangerous regime where your physics is truly partial physics. It's not like a simple kinematics problem where the physics is fairly good. What happens if the physics is really hard? And this is where I think machine learning will have a lot more impact if done correctly, when you work on very difficult physical problems. So I'm going to change gears, and to further perhaps motivate people to look in this direction, what I'm going to talk about in the next few slides is something that we worked on as a paper in ICCV, then it was turned into a startup, and then it received funding, and now there's quite a few employees in the Bay Area. But it really starts with this plot again, looking at where you are on this plot, and then analyzing sort of a key industry that is very useful. And one of those industries is 3D cameras. So we talked about LiDAR. The last talk was very exciting. It discussed a lot of sensing. A lot of people have come up to me to talk about LiDAR. And can anyone give an explanation of how LiDAR works? Fantastic. So LiDAR, a lot of companies in Silicon Valley do LiDAR. Basically, very simple abstraction. You have a laser, it sends a short pulse, light travels there and back, and that takes some amount of time. Right? Light travels in about 1 nanosecond, light will travel 1 foot. So if that wall is 30 feet away, it's going to take 60 nanoseconds for the light to go and come back. And so this is how state-of-the-art 3D sensing systems work. It's basically really good engineering on top of that abstraction. And so with this kind of technology, for example, LiDAR, you can look at how this is the engine that powers autonomous driving, how this may power surgical robots, and also types of manufacturing. The fundamental idea is that you're capturing the XYZ position of light reflections as opposed to a 2D camera, which is just XY pixels. So let me jump right in and just show you an example. This is a coffee cup in the corner of my office, and it's white and it's got these fine grooves on the surface. And you want to obtain a 3D scan of this coffee cup. You want to get the geometry of this coffee cup, so you might use something like the Microsoft Kinect. It's the latest model, well-engineered device. Does anyone know what raise your hand if you've heard of the Kinect before. Great, it's a workhorse in computer vision. It's the de facto 3D approach, and this is what the scenes will look like if you scan them with the Kinect. You get a higher fidelity rendering of the coffee cup. You see the geometry. You see, sort of that curvature of the whole cup. But you can see there's a lot of noise on the surface, and the region where those grooves are, that detail has been lost. Nothing we do in image processing. It's a class that I teach, so I'm sad that we can't do it. But nothing we do in image processing is magically going to put the data back. Once you have lost it on the capture side, you have lost that information. So we took the coffee cup down to the basement where we have a high-end machine shop. And in this machine shop, we specifically have a special laser scanner there just so we can scan parts at extremely high fidelity. Because after all, they have to go into amazing robots at IISC, right? You need them to be at good tolerance. And so you scan it with this multi-stripe laser technology. We won't go into the nitty-gritty, but basically it's this very expensive fixed working volume device, and this is the scan that you get. And you can see that this scan is better than the Kinect. It better be, right? It's 10 times the cost. But you can still see that the grooves have been lost. And now you've lost all your real-time performance and everything like that as well. So the question is, can we invent a new type of 3D camera methodology using principles of both AI as well as physics? Can we invent a new type of technology? And we're going to do this by blending the physics of polarized light with artificial intelligence to obtain a result like this. And this is arguably a higher quality version of the scan, but if I zoom in on that region with the grooves, that's where the difference is most visible, where you can see that each and every groove has been preserved with high fidelity, while the regions that are smooth are left smooth. So 3D++, there's a lot of, if you can sense the world in 3D at this level of photorealism, then you can just imagine how this would look on drones. Now drones aren't just avoiding obstacles, but maybe they can start to look at expression of pedestrians, right? Look at the fine facial wrinkles when somebody frowns, and start to analyze the emotional state of drivers. Of course, I promised you some physics, and it's here. There's some polarization of light. I'm sure we have all forgotten. Once we get into college, we forget about the physics that got us there. So light is an electromagnetic wave. It's got an electric field and a beta field. So when we talk about linear polarization, we say, okay, you know what? We're just going to ignore that oscillation field of the magnetic, and we're just going to define polarization as the rotation of the electric field in space. So for example, a wave like this will have a plane of polarization somewhat in this angle. If I have a wave with a different state of polarization, then it would be rotated, right? So it's a rotated plane of polarization. In short, polarization gives you the rotation of light waves in the world. Where this becomes very interesting is in the context of reflections. So if I have light incident on this surface, for example, it might strike the water. Now you can see that there's dots and hashes in the line. The dot means that the oscillation rotation is out of the board. The light is oscillating out of the plane of the board. The hash means it's oscillating within the plane of the board. And so you've got both in-plane and out-plane oscillations as the light strikes the surface. But as the light leaves, you might have something different. You might just have oscillation out of the plane of the board. Again, for one bonus point on this hypothetical exam, does anyone know this effect? The name of this effect? Is anyone optically oriented? Polarization, that's right. Let's have a little sidebar. Why is the sky blue? Rayleigh scattering, good. Okay, so that I heard that answer. That's not this explanation. But this explanation is something called Brewster angle. Now who's heard of that? Yeah, okay. So Brewster angle essentially tells you this. So you can see under the water if you have your Brewster angle just right. So if you wear sunglasses that are polarized, you can actually see underneath the water glare. Just a fun fact for life. So anyway, you have the Brewster angle that's coming off here. And so what this tells you is that there's something very special about how the material deflects these angles, right? There's a signal here. There's an input where it was one polarization state, and there's an output where it's a different polarization state. So there's a subtlety in that change, which depends on something with the water. So maybe that applies to this coffee cup. So we can take pictures of the coffee cup at different polarizer angles. And this is where the special taste of the visual machines group comes into play. We look at how the camera itself can capture new forms of higher dimensional data. So now we're taking additional pictures at different polarizer angle rotations. And I get these 3 photos at 3 different polarization angles. Now this might not look too special, so let me blow up the 2 most dissimilar photos. These are the 2 most dissimilar photos. And if you were working on a project in my lab and you were looking for a signal, what is the first thing you would do if you saw these 2 photos and you're trying to see if there's a hunch that you can pull something out? Exactly, just subtract the 2 images. So you subtract the 2 images and then you end up with this. You end up with almost nothing, so there's very, very, very little signal. Now, a lot of times I bring up this example because I once had a student come to me who knew a lot about neural networks, but didn't know much about imaging or cameras or what the dynamic range was. There's a subtraction here. The subtraction is slight. So you have a lot of values like on an 8-bit scale from 0 to 255, you have a lot of values like 3, 4, 6, 7, and so on. So of course you need to tone map it to the full dynamic range that you're looking at, right? So if we do that and it's tone mapped to 8 bits, then we end up with something that looks like this. Still not much. Right? Still doesn't look like that photorealistic geometry I showed you, but at least there's something there. And so that something actually turns out to be very difficult physics. It turns out to be very difficult physics that models essentially how different light waves at different angles with some scattering going into a medium relates to the slope of the surface. And we're going to try to recover the slope of the surface. Now, solving this equation in closed form requires assumptions. You need to know things that you don't know about objects, like the refractive index or the materials. So in short, it's sort of unsolvable. So now you've hit a wall. And that's the wall, right? That's why people build Kinects, and that's why the industry builds structured light sensors and stereo cameras. So how do we overcome that wall? Well, we overcome that wall by turning to a more software-oriented playbook, to going back to this playbook of unifying physics and artificial intelligence. Now, the blending is subtle. It's not just you smash things into a neural network, because now we have high school students that are doing that and middle school students, especially in the Bay Area. You can't just smash things into a neural network, but you need to blend these in a certain way. It's hard to blend them because unifying an idea like polarization, which is from Fresnel's time, 1800s, is hard. it's incompatible math, and we're talking about two fields that don't talk to each other, optics and computer science. And so just to cut to the chase, what we ended up doing was fairly simple architecture. We just built a dual stream convolutional neural network where essentially one stream of the neural network takes in rendering predictions with a physics-based engine. And we essentially have enough layers that we come up with an embedding space such that the physical model can be compared with the actual image data. Okay? So those are the two keys, having a decent rendering engine and coming up with an embedding space such that these two models can be combined. So you can think of it as a special form of sensor fusion. And if you apply these types of ideas, you end up getting essentially surface normal quality that either meets or exceeds this. So the latest paper is on arXiv, and you're welcome to check it out. Now, this playbook doesn't just apply to building better 3D cameras, right? You can take this playbook and you have a recipe for doing interesting things. So this is some stuff that actually some of my undergraduates led. And my undergraduates were building a physics-based way to see around corners in real time. So this is the first method that if you look at this left-hand side image, there's a wall here and there's an occluder. Take my word for it, but there's actually this person behind the occluder. You can't see them, and that's the point. So you have the same view as the camera, but the camera is somehow able to see that person on the right-hand side and in addition estimate their pose in real time. We can tell if they're sitting, standing, holding a thumbs up, or doing rock, paper, scissors. So just recently, a couple weeks ago, my undergraduate students were very passionate about the impact this could have for hopefully one day predicting traffic accidents and making, traffic accidents less likely. And so they built this demo and showed it off, and we were very lucky that they were able to win an award for their work. They won the best demo award. And so the engine here, this wouldn't have been possible without that fusion, again, of physics and machine learning. Another way to look at this is medical imaging. One of the most important problems is how do we deliver healthcare in rural areas? For example, in India, tuberculosis, for example, is a cured disease. We have a cure for it, but the diagnosis is somewhat challenging because many times it requires an X-ray. An X-ray is great in the developed world, but not always a luxury everywhere in the world. And so this is a very special type of X-ray sensor. So we're still using an X-ray source. The source is still being used, so half the battle is there. But in this recent work, what we're doing is we're actually taking a document scanner. Some of you may be too young to remember document scanners. Now we just take pictures with our phone. But back in the day, we used to have these desktop document scanners. Right? I have to use all this back in the day stuff when you become a professor. But back in the day, we used to have these document scanners. And you put essentially a sample on the document scanner. And so here we've put a human hand, and you have some specialized optics, and you're able to end up with an image of the hand. So that's a hand, a cadaver hand. So it's been chopped off and frozen and then wrapped in a latex glove and laid on the bed of a scanner, right? And there's some scintillation optics there, but the bottom line is you get a very noisy image. And so really what's happening to get that image on the right is we look at the physics of how that noise is being generated and essentially denoise and deblur it. It's a pretty classic imaging problem, but it's aided by use of the physics. So I've shown you a bunch of broad ideas that you can start to do if you start thinking both on the sensor side as well as the software side. Okay, and that's what makes our group unique. But there is one thing I do want perhaps you to take away from this, and it may tie in with some of the previous talks today. And that's that the mathematical engine that underpins these papers is actually one word. It's, the one word that I think is most important in the work that we do is regularization. We talked about regularization today, so who can define regularization? That's a great answer. So the answer he gave was that regularization is something that reduces overfitting by penalizing the degrees of freedom on the weights. That's not an incorrect answer. However, it's a very machine learning centric answer. It's somebody who watches a lot of Andrew Ng will come up with an answer like that, which is the right answer. It's there's no technical incorrectness there. However, regularization is much, much beyond just applying dropout or L2 regularization to a neural network. That is actually a subset of the magic of regularization. Regularization is the idea you have an objective function and you can apply any type of function to that objective function to penalize the forms that a solution might take. It doesn't just need to be in the degrees of freedom to reduce overfitting. For example, in a physical basis, you might want to have your solution to be close to the physical prediction, right? Sparsity is another way. You can have your solution be sparse, something called compressive sensing. So there's a lot of really exciting avenues to go to with regularization. In segmentation and denoising, for example, people can use like graphical models, analogies to apply Markov random fields as your regularizer, right? To denoise based on a neighborhood. And so if we look at the mathematical form of regularization, this is what it takes on, right? So let's consider a concrete example. Imagine A is a convolution operator, right? So it looks like a Toeplitz matrix. So if we have a Toeplitz matrix, and we might have a blurry measurement that's B, right? X would be like a sharp image, B would be like a vectorized blurry image that you measure, and A is an operator that applies to the data, right? So that operator would be, for example, in this case, a Toeplitz matrix. Does this make sense to everyone? So raise your hand if this makes sense. Toeplitz matrix. Okay, very few. So I feel I can say this because I am sort of in your generation. It is very important to master the fundamentals of convolution before looking at convolutional neural networks. Toeplitz matrix is how you apply discrete convolution. It's one way to apply discrete convolution. Circulant matrix is another. And so you can apply these matrices, and when you regularize it, so which one of these three equations involves regularization? Okay, raise your hand if it's the first one. Second? Okay. Third? So second and third. Second and third all include regularization. Which one enforces sparsity? Third one. Okay, what does the gradient mean? What does the gradient enforce? Does anyone know the third problem is a very famous problem? It can be solved using lasso type of methods. That's a good explanation, but it's the total variation denoising. You're penalizing that regularization term where you're not regularizing the L1 of x. You're regularizing the gradient of the L1 of the gradient of x. So it's different than regularizing just x. And that's what makes it actually magical. So if I show you an example, so typically when you do something called deconvolution, you deconvolve a signal to deblur it, right? So when you apply deconvolution in the naive way, you might apply the first row. Okay? You might apply ax minus b. That's what it comes down to in a linear algebra sense. And so if I look at what that looks like, so on the top left I have a blurry image, and this is on the left side what happens if you just do ordinary linear regression, basically without doing any advanced regularization. On the right side, if you do some clever regularization, you end up with an actual result that you can use. And so there's a subtlety to how you design regularizers. And ultimately, it's up to you which area you want to specialize in, but I highly recommend gaining some expertise in regularization because it's used in a lot of areas, not just machine learning. So ultimately, we have a group at UCLA. I know many of you may apply to UCLA. Please do. We have great weather year-round, much like Bangalore. We also have palm trees. So I did my PhD in the East Coast where it was very cold. So I love UCLA, and I'm sure many of you will. And really, all this talk is the work of the students. So I highly encourage you, those of you who go to CVPR. CVPR is in Los Angeles this year. Who's going to CVPR? Anyone? Yeah, it is a long flight. But for us this year, it's in our backyard. And so we're really excited about that. So if any of you do happen to go to CVPR, do stop by and say hi or come by for a visit. So thanks so much, and I look forward to working with you over the next week.
Hello, sir. My question is, using the LiDAR scanning or Microsoft Kinect, It actually captures the the data in the like what we get in the 2D picture. So if let us say we capture of the same cup or any scene, then if we capture it using multiple Kinects or multiple LiDARs, then if we get it back together, what would be the complications, and how do we get it without what do you call that? Very seamless and with the linear flow.
Yeah, it's a great question. So how do you essentially take multiple Kinects, capture point clouds, and stitch them together? Is that your question?
Right.
So it's a very good question, because when you have an augmented reality device, many times you have a 3D camera, so as you're moving around, you're actually stitching together all the different views in time together. It's the same problem as if you had multiple cameras. So there's a variety of algorithms to do that. The classic one is iterative closest point, ICP, if you want to look at that.
The method using polarization, will it work for objects which are not rotationally symmetrical?
Yes, so there's a unique surface normal that's obtained under this method.
So, okay.
Previous methods do struggle with the symmetry problem because there's 180-degree symmetry in the polarization angle, right? If my filter rotates by 180 degrees, I get the same image because that's the essentially frequency of the polarized light. So essentially part of our contribution was coming up with a way to overcome that. And that's what part of the neural network is doing.
Hello, sir. The method which you showed just now, by that method, with the help of that method, can we calculate the depth of the image or the dimensions of the image, and that will be in the real time? Can we use that thing?
Yeah, so like I said, there's a company that's working on that now, and so they are transitioning that away, and that's their goal essentially. When we implement the technique, many times in research, we don't really care about optimal performance, and so we were slightly below real time. And so they are working on taking it to real time with parallel computing, essentially.
And in comparison to that method, with the stereo cams, so which one will be the faster? What do you think?
That's a good question. I think with stereo cams, a lot of it is dependent on the resolution that you're looking at, whereas this is not as resolution dependent. And with stereo cameras, a lot of it is also dependent on the sparsity of your edges. So ultimately, stereo cameras require you to dimensionality reduce your scene to a set of sparse textures. And in some scenes, that's difficult to do. So I guess the answer is it's sort of scene dependent, and it's something that we do, if you were working at the company, that would be like one thing that you would want to benchmark so that analysis was done. So it's a great question. I don't know the exact answer.
Sir, we were not able to capture the details. It was because the object was translucent or the details were too minute?
Which example?
Like the cup.
So you weren't able to capture the details with the Kinect because the details were too small. They're on the orders of 100 microns or so on that order. So the reason it doesn't work with, let's say the Kinect, just very briefly, the problem with LiDAR, why it's fundamentally not the solution to capture detail, is because of what I would call is the cursive speed of light. The cursive speed of light is as follows. So that wall is 10 feet away from me, right? So light takes 20 nanoseconds to go there and back. Now imagine I had a billion FPS camera, billion frames per second camera. Billion FPS means that every frame is captured in 1 nanosecond. That means in time, every frame skip gives me 1 foot of range resolution. So the industry has done a very good job of making the cameras faster, right? It's faster and faster and faster, 10 billion, 100 billion FPS effectively. But still you're limited to a few millimeters to up to a centimeter. There's only a limit to how fast you can make the cameras. And I think LiDAR has hit that limit in terms of speed. That's why you're very rare to see LiDAR giving high resolution surface detail.
Thank you, Achuta.